Hello and welcome to our demo. We're the ECE 492 CHDS2 capstone team. My name is Luke Kapeluck, and my teammates are Anthony Dmytryshyn, Hongru and Kevin Wedage, and our client is Stephen Knudsen. Now, nobody likes to be told to constantly social distance, even if that's the right thing to do. The COVID-19 haptic distancing system is an automated system to do all that just for you. It consists of a wearable Bluetooth device paired to a user-friendly Android application, such that when you approach another user 3 meters away to 2 meters away, the system will provide variable haptic feedback alerting you that you are no longer social distancing. As part of the CHDS team, we were expected to do just that, and we've delivered. Our project also allows for home locations to be set via geofencing where the system is to be disabled because they are considered safe. And now, to talk about the hardware of our project, here's Kevin.
The hardware consists of four components. The MCU is the Arduino MKR 1010 Wi-Fi board. This contains the Bluetooth functionality and communicates directly with the Android smartphone. The Arduino is powered by a power bank, but can be also powered by a LiPo battery with the supported JST pins on the Arduino board. The other main component is the vibrating disk motor. We found that the Arduino could not provide sufficient current to power the disk motor alone, and as a result had to use the Adafruit motor driver as the intermediate device. The 4 pins on the disk driver are directly connected to the corresponding pins on the Arduino board, and the 2 final pins are connected to the vibrating disk motor.
Here is our home screen of the COVID Haptic Distancing System Android application. The user will be able to access the important features by clicking on either blue bubble. To initiate the connection process to the haptic device, we can click on the top blue bubble to manage the connections. When we navigate to that next screen, here we are greeted with a single option to search for devices, as nothing is yet connected to the app. After clicking on the button, a dialog appears with possible haptic devices we can connect to. As shown, currently we have the choice to connect to CHDS or CHDS2. After clicking on CHDS2, a connection is formed and basic statistics are shown, such as the device name and MAC address that we are connected to. As well, once the connection is successful, a small vibration is sent to the haptic device to indicate a successful connection process has occurred, and that is represented by the last command sent statistic. In the live demonstrations following this clip, the vibration is not quite visible due to it being taped to my arm and my body always moving around. As shown in this clip, however, the device is fully capable of vibrating when told to by the app. In the following clip, it is a live demo of me and, courtesy of my brother, showcasing a basic interaction when using the COVID haptic distancing system. Here, you can see me standing on my phone having the COVID haptic distancing system app open on the connection screen, while the haptic device is taped to my arm. As my brother begins to approach, the vibration level will change from the hex code 5631 to 5632, indicating that he has now come from within the 3 meter range, but outside a 2 meter range, to within the 2 meter range of me. The last command changes value from 5632, which indicates a strong vibration signal being sent to the haptic device, while 5631 indicates a weak vibration being sent. At this point, you should be aware of the vibrations and move away from the other user, as he is breaching COVID regulations and is now within your personal space.
So here is another important feature of the app, geofencing. By clicking on this button, you can get your current saved active geofencing locations, and as you can see, it is empty right now. So if you click on the Add button, a Google Map will pop up with your current geolocation. You can use the search bar to search for locations, or simply long-click the map to directly choose a location from the map. And then we can specify the location name and radius. The latitudes and longitudes are automatically generated using Google Map API. And use the Save button, we can save the location. And now a new geofencing location is saved and it is set to be enabled by default, and we can use this toggle button to change. If you click on this item view, you can update your saved geofencing location info by clicking on this update button, or you can just use the delete button to simply delete this geofencing location. And now we will give you a quick live demo about geofencing. As you can see from the video, Anton and his brother are within the 2-meter distance and the haptic device is currently vibrating. However, if we turn the geofencing location of his house on, as you can see from the video, he turned it on, the haptic device stopped to vibrate immediately as the geofencing is enabled. And if we turn it off again, the haptic device will start to vibrate immediately as well. So basically, user can decide if they want each geofencing location to be on or not.
When you are done using the COVID haptic device, you should disconnect from it in order to save your phone battery, as constantly scanning for new Bluetooth Low Energy haptic devices in the background can put a strain on the battery over time. By clicking on the disconnect button, the BLE connection is broken, and you are free to connect to other devices. If I attempt to connect to another haptic device again, CHDS2 pops up, showing that we can reconnect to our previously connected device if we want to. Some issues we had with the project involved creating Bluetooth Low Energy connections and maintaining them, due to the lack of well-written documentation on the official Android website. On top of that, Android adds on restrictions as to the amount of time you can spend scanning in the background, as well as how many times you can initiate Bluetooth scanning within a time frame. Also, using the accuracy of the RSSI distance is inaccurate by itself due to it being device-specific. Despite these problems, however, we managed to overcome them all to an extent. For maintaining Bluetooth Low Energy connections, we implemented a first in first out thread safe queue in which different Bluetooth operations are queued and executed one by one when the corresponding callbacks are given. This is due to an interesting observation where if two operations are called one after another without using the queue, and without waiting for a successful callback from the first one, then the second operation seemingly falls into a black void, as if the code was never called in the first place. The FIFO queue prevents this from occurring by waiting for the callback and only executing the next operation when the first one finishes. As well, if we start scanning for background devices 5 or more times within a 30-second span, the OS prevents you from initiating any more scans for an unknown amount of time. Since our app starts scanning for other haptic devices whenever a successful connection occurs, assuming you don't disconnect and reconnect to the device 5 or more times within 30 seconds, then this issue should never occur to the user.
The project, of course, had some things that didn't work. We've mentioned this one before, but achieving a 10 centimeter accuracy was one of our primary difficulties, given that measuring distances using RSSI values is notoriously inaccurate. When testing the system, we were finding that a device 1.5 meters away was receiving RSSI values saying it's anywhere between 1 meter away and 7 meters away, which could be very bad for our system. Now, we've done a lot of work and a lot of math, including math not done or thought of before, to try and fix this large inaccuracy when using RSSI signal strength. Shown here is my whiteboard containing the math and the idea behind it. We used a moving average of RSSI values given a period and a rolling standard deviation calculated iteratively, which I've not seen anyone do before. The RSSI values over a certain period of time determine an average and a standard deviation, and any value received outside of a standard deviation were adjusted to make the system more accurate. In the end, the system on average has a 10 to 20 centimeter inaccuracy, which we believe to be very good given that we're working with RSSI.
As of right now, the COVID haptic distancing system does not include contact tracing. In the future, we plan to incorporate this into our system. This will include the option to report if you have COVID and the ability to receive notifications if someone you have come into contact with in the last 2 weeks has reported they have COVID. The behind-the-scenes infrastructure would include setting up a cloud server that has database and REST API functionality. In addition, we want to design a more consumer-friendly enclosure for the haptic device. This would include 3D printing a casing and supporting multiple watch bands.
And that concludes our final presentation. So to do a quick little summary, our product in the demo is an Arduino MKR Wi-Fi 1010 microcontroller prototype connected to a LiPo battery. This is paired with our Android application. Our system can be enabled and disabled based on set locations using geofencing, and when the system is enabled, the wearable device will provide haptic feedback depending on where the other person is. Stronger feedback will be provided at the 2-meter range than the 3-meter range. We had a few things that didn't work and some others that worked well. Namely, the RSSI and Bluetooth related functionalities came with their problems, but the rest of the project came out very well. For the future, we would work on contact tracing and improving the distance measuring accuracy. I'd like to thank Stephen Knudsen as our client and Stephen Fan as our technical advisor, as well as all of you for listening. Now, I'd like to open up the floor to any questions you might have at this time. Thank you.